some basics of electricity and magnetism, or we can say uh, not basics of electricity and magnetism, but we discussed some mathematics which is required to understand uh, electricity and magnetism or electromagnetism. So we started with this new operator, with this new mathematical operator, differential operator, and we talked about fields, scalar fields, vector fields, and we talked about how we require and why we require this del operator, because we are interested in knowing how these fields they behave and how they change. So to find all this or to know the nature of these fields, we operate with this operator and we see what is the change in our field. And for that, we have developed this mathematics where we said that our del operator is a vector differential operator, as it is a vector differential operator. So we can operate with this operator both on scalar fields as well as on vector fields. There is one type of operation, or we can say that gradient of scalar. There's only one way how we operate with this operator on a scalar field, and that way is, or that is called gradient of a scalar. There are two ways how we can operate with this operator on vector field, and those two are divergence of a vector field and curl of a vector field. And the physical significance of all these operations is important, or the resultant field produced when we operate with this operator on any field, we get the resultant field, and that is what we significance is important. So what is the significance of that? So we said that gradient of a scalar, it becomes a vector field. It is a new field, vector field, and this new field, magnitude of this new field, we need to know, we should know, and what is direction of this new field that we are interested in. As we know that electric potential is a scalar quantity and it produces scalar field, and when we find gradient of this, then that is another field, and that field is what it is, vector field, and it is electric field. So the significance is what it is in the direction of this field, new field is in the direction of in the direction perpendicular to the plane where v is constant. So you see it from your previous knowledge as well, that if we are representing uniform electric field, then it is represented in both ways, by drawing simply electric field lines or by drawing these equipotential surfaces. So then we said that you can practice number of problems on this, so that you become master of operating with this operator on different fields and do any problem which we'll be facing. So divergence is what is it is related to outflow of field. It is related to how it diverges, field diverges. So more is the divergence or more is the outflow, that means more will be this physical quantity, and it is as it is divergent. So it is what it is. It is a scalar quantity. In electricity, it is related to what, or in electrostatics, it is when we say divergence of electric field, which is or through any area, if we see how much field is crossing or flowing, that is what it is a flux through that, and it will we can relate that with this divergence of electric field. So as you see it in Gauss law of electrostatics, we'll do that in today's lecture. We'll try to write that Gauss law, because divergence ही हम find कर रहे हैं. Gauss gives you what? Gauss law gives you what? It gives you divergence of electric field. So how we can write? अभी तक हमने we have written that in the form of integral form, where we say that E dot ds or closed line integral of electric flux or electric field is electric flux. Okay, so we'll see that and operation of this del operator on this means on vector field, which is divergence of a vector field. Mathematically, how we do it, that is given and that we discussed. Okay, so it is simple derivative of x component of field with respect to x and total derivative of a component with sorry y component with respect to y and z component with respect to z. Okay, negative divergence means what, positive divergence is what, and what is zero divergence. We discussed all these cases and you are familiar with what these are. Then we have another thing we want to measure, that is rotation in our field. So for that, to measure rotation, what we do is we take curl of our field and we see if curl is zero, there is no rotation in the field. And if curl is non-zero, that means it is rotational field and there is rotation, and we can measure that, and mathematically it is curl of E. And then we operate with this operator and then we find this determinant and we see different components of the resultant field. Now this is a new field which is curl of E field, and that gives you idea about the rotation or circulation in the field. And I said that two important theorems which we'll be using while dealing with electric and magnetic fields, or while converting integrals from one type of integral to the other type of integral. These are pure mathematics. This is pure mathematics or concepts of mathematics. So simply, I'm without giving proof or without going into much details. So I said that there are two theorems. So one is called Gauss divergence theorem, because the divergence of electric field is involved in this, and another is Stokes theorem. So according to Gauss divergence theorem, we said that closed line integral, sorry, not line integral, whenever we have closed surface integral of any vector, that can be related to volume integral, not volume integral of that vector, but it is volume integral of divergence of that vector. So this is my Gauss theorem. This is Gauss theorem. So it is what? It is surface integral to volume integral. It relates surface integral to volume integral in this way, that A is replaced by divergence of A. And we have Stokes theorem. It is about line integral of vector field, and it is not only line integral, but it is closed line integral. So closed surface integral is related to volume integral, and closed line integral is related to surface integral. So it is closed line integral of any vector is surface integral of कर्ल ऑफ दैट वेक्टर. ओके, तो ये आपको दोनों याद रखनी है. एंड देन there are some examples. As I said that if divergence is zero, that means inward and outward flux दोनों बैलेंस हो रहे हैं and net flux is zero, and that is what that is, जहाँ पे जो field है that is solenoidal field. It is है ना, in circle going out of the closed surface, then again coming in, going out, coming in. So that type of field is what it is called solenoidal field. And we have a rotational field when there is no rotation in the field. Curl of field is zero. So that is a rotational field. Let us see some pictures and try to predict what type of field this is. I have this. It is what field is represented by these parallel equispaced arrows. Okay, so we can see there is no circulation in this field. Can you see any rotation, any circulation? No circulation in this field. And what about divergence of this field? Divergence is, can we see divergence?
Zero.
There is
Zero divergence.
Zero divergence. Why zero divergence? Because you can see that if you draw any closed surface, so you can see that inward flux is equal to what? It is equal to outward flux. Okay, so इसलिए we can say that this is what this type, this is what type of field it is. There is what? Divergence is zero, means it is solenoidal. Field कैसा है? Solenoidal field. और कर्ल क्या है? That is zero. Curl is zero means it is, there is no rotation. So it is solenoidal irrotational field. We call it solenoidal irrotational field. Let us see another field. This is my field. Field lines, they are diverging. You can see divergence. ठीक है? तो moving outward, outflow of this field. So we can see what? We can see that divergence is non-zero. So it is not solenoidal field. It is non-solenoidal field. And what about curl? Can you see any curl in this? Any rotation in this field? Any rotation in this field? There is no rotation in
No,
this.
sir. No, sir.
Okay, so what we call, we can see that divergence is non-zero, divergence is there, it is non-zero, and curl is zero, there is no rotation. So it is non-solenoidal, neither solenoidal and nor rotational or irrotational field. Let us look at this. This is what this is. You can see that there is some circulation. Okay, circulation hai. Is there circulation? Yes. Is there any divergence?
No.
No
No,
divergence. So we can see that divergence is zero and circulation is there. So that's why it is curl is non-zero. So we can say that this is solenoidal because divergence and this is divergence is zero and it is rotational field. There is some rotation. Last example is what it is. You can see this is what there is circulation and it is also diverging. You can see some divergence. Okay, so this field is what? Divergence is there and we have what? We have curl is, circulation is there. So this is neither solenoidal nor irrotational. Now let us start with the basics, or you can say with whatever you have done earlier, but in a different way, because now we have del operator. It will be replacing integral operator. The basic idea is, and why we are doing this, because it is easier to use del operator, and mathematics becomes easier when we use del operator or differential operator than integral operator. So we are replacing integral operator by a differential operator, and we'll be writing what? We'll be writing 4 fundamental laws of physics, which are which you have seen, which are also Maxwell's equations. They are called Maxwell's equations. Maxwell's equations are nothing but they are 4 fundamental laws. They make Maxwell's equations, and they support what? Maxwell's equations, they support this unification of 2 different branches, electricity and magnetism. Because we'll see that in जैसे जैसे हम ये laws को करेंगे. So you all understand what is Gauss law of electrostatics. It is about electric field and it is about electric flux. We say that if we have a closed surface, this is closed surface and this is like sphere, and this closed surface is enclosing some volume inside it, and then we talk about flux through this closed surface. And to find flux, you know that flux is what? It is dot product of electric field and area. If we find flux through any open area, if it is not a closed area, let me draw, this is some rectangular shaped area. So you can see that electric field is linked here, or it is there. So you can see what is the flux. Flux depends on strength of this field. More crowded lines means more lines will cross through this. So it depends on the strength, and it depends on area. Bigger is the area means more will be the flux through, and it is dot product of these two. It depends on orientation of this area with respect to the field. When it is perpendicular, area is perpendicular, means plane is perpendicular, and area vector is in the direction of electric field, then we say that you know all this, then this is what it is. So we say that flux is what it is dot product of this, and in this case This is a closed surface area. I choose a small surface area on this closed surface area, and I say that flux through this, and I say that electric field strength at this point due to charge enclosed by this is E, and then I say that E dot ds gives you what it gives you, small flux. It is what it is, not total flux through total, but it is through small area ds. So it is this, and integrating this over the whole area, and the area is closed area, so ds is part of that closed area. So I can write that this is what, this is total flux through this closed surface area, and this is predicted by Gauss what this flux is. And किस कौन से फैक्टर्स पे ये फ्लक्स डिपेंड करता है, दैट फ्लक्स थ्रू एनी क्लोज सरफेस is proportional to what, or it is what it is, it depends on whether if it closes no charge, then there will be no electric field lines and nothing will flow out, and you can say that it is zero. Even if there is presence of charge but it is outside this, it is not enclosing any charge, then we can say that it is what, it is zero. But if it encloses some charge, then we say that it is what, either from that charge lines will diverge or it will converge towards that charge. So you can see that flux will be there, either it will be positive flux or it will be negative flux. And then this integral, that is closed surface integral of electric field, is what, it depends on charge enclosed by the closed surface, and it also depends on what, it depends on medium around this charge or medium within this enclosed by this surface, closed surface, because electric field strength, it will be accordingly more or less. So we can say that it is what it is. It is what, it is Q divided by epsilon naught. This is our I have explained what we how we find flux. So this is our Gauss law, that flux of any this field is directly, electric field is through closed surface is directly proportional to total charge contained within that surface. Now let us go into more details. Let me see what this charge is, and let me say that it is some charge. It is not a point charge, it is a charge which is distributed over this volume. So it is what it is, volume charge is there, or volume charge density we can define for this. This is rho, it is volume charge density, means charge per unit volume of this Q. So it is volume charge density. Okay, and I choose small portion of this, that is dV. This total volume is V, and I choose small portion of volume dV. Then I can find what is the amount of charge in that small dV volume. So rho is the charge per unit volume times volume gives you charge in that volume. So I can say that small charge enclosed by this, or not enclosed, on this dV volume is what is rho dV. And total charge Q inside this volume V, or in this is what it is, integral of this rho dV. So I can say that this is what, this is charge Q can be written in terms of volume charge density like this. So let me replace what, let me replace this by 1 over epsilon naught times volume integral. This is now volume integral of volume charge density rho. So now I have two integrals, as we said that we can relate surface integral with, so we can do what I want. This is volume integral on right hand side. I also want volume integral on left hand side, so that I can equate their integrands. So I can use Gauss divergence theorem, because Gauss divergence theorem, that it relates closed surface integral of any vector to the volume integral of divergence of that vector. So for this I can write according to Gauss divergence theorem. E dot ds or dA, it is only notation difference, it is area, is equal to, according to Gauss divergence theorem, it is volume integral of divergence of E vector. So I can write here this, and this is equals to, so I have divergence of E, this is equals to 1 over, or let me write it as volume integral of rho divided by epsilon naught dV. So simply by writing, this is my Gauss law, I write it in the form of volume integral. Volume, this is charge is what it is, not a point charge. It is distributed over volume V. Then I can write that this total charge Q can be written in terms of volume charge density as this. And using Gauss divergence theorem to write left hand side of this integral, or sorry, left hand side, which is this integral, in the form of volume integral by simply using Gauss divergence theorem. So I can see I have volume integral on both the sides, and this is integrand on left hand side, and this is integrand on right hand side. As volume dV is what it is, arbitrary volume, we can equate integrands on both the sides. So I can write that divergence of E is equals to rho divided by epsilon naught. So my integral form of Gauss divergence theorem is now what it is. There is no integral in this, and I have what I have, Gauss divergence theorem, same Gauss divergence theorem. There is no change in Gauss divergence theorem. Meaning of this is same, everything is same, and but it is in differential operator form. I have del operator is involved here, and it is divergence of electric field is equals to rho divided by epsilon naught. Or I can also write this as divergence of, let me cross multiply this epsilon naught to this side, and I can write this as epsilon naught E equals to rho, and this is a new vector which is called electric displacement vector. We'll talk about this later. So this is what divergence of D, that is electric displacement vector, is rho. This is what this is, new form, same Gauss divergence theorem. Sorry, same Gauss law of electrostatics, but in a different form, or in a differential form, you can say, in the form of del operator. तो ये हमें ज़्यादा यूजफुल है. वी विल यूज दिस फॉर्म ऑफ गॉस लॉ to do further mathematics. Then we have Gauss law of electrostatics. It is about not electrostatics. It should be Gauss law of magnetostatics. Okay, continue. Okay, we have proved this. We skip this. Now we have Gauss law of magnetostatics. It is about magnetic flux. It is about magnetic field. So same law in for magnetic field. We have what we have, closed surface area, and we can find flux, magnetic flux, to this small area, and that magnetic flux is B dot ds. It is small magnetic flux, d phi you can call it, and total flux through the whole area, closed surface area, it is B dot ds closed surface integral, is total flux q, and total flux, or this magnetic flux through closed surface, is always zero. Why it is zero? Because monopole does not exist. If we say that there is some north and some magnet is there inside this, so it will be having north and south poles. So it is having both polarities. वहाँ पे भी अगर इलेक्ट्रिक डाइपोल ही एग्जिस्ट करता तो हम कहते हैं कि इलेक्ट्रिक डाइपोल इज द यूनिट. सो इट इज नेगेटिव पॉजिटिव बोथ चार्जेस, इक्वल एंड ऑपोजिट चार्जेस. तो इलेक्ट्रिक फ्लक्स भी हमेशा जीरो. सो यू कैन से दैट ये गॉस लॉ ऑफ इलेक्ट्रोस्टैटिक्स होगा if free charge does not exist, if Q does not exist, but it exists like dipole, we have both the polarities positive as well as negative. तो ये हमारा Gauss law of electrostatics बनेगा, but it is not there. We have positive as well as negative charge, or individually they exist, not in the form of dipole. So we can say that we have negative flux, we have positive flux, and we have also zero flux. So, but here monopole is not possible, monopole does not exist. So we cannot say that we have only one polarity, one pole, that is north pole, and due to that north pole, flux is positive, and due to south pole it is negative. No, we have both. So that means flux is what it is, zero. And again, we do the same thing. We are interested in writing this in differential form. This is integral form of Gauss law of magnetostatics. And same we can write in differential form without any change in the Gauss law. And for that, we again use Gauss divergence theorem. And using Gauss divergence theorem, I can convert this surface integral into volume integral. And then I can write this as volume integral of divergence of B. So my left hand side is now what it is, a volume integral of divergence of B, and this is equals to 0. Again, you can see I can equate it to 0. So I can write that divergence of B is 0 is same as closed surface integral of B is 0. There is no difference between these two equations. Only difference is that is in differential form and this is in integral form. So I have two equations. I have written two fundamental laws of electrostatics or electromagnetism. One is divergence of E is equals to rho divided by epsilon naught, and another I have written divergence of B is equals to 0. Both these are about electric flux and magnetic flux. So ये divergences हैं electric field का divergence, and this is divergence of magnetic field. Okay. Now let us go to another law. We are doing these are laws which are called Maxwell equations. है ना? तो हम Maxwell equations की बात कर रहे हैं. These are first two Maxwell equations. Gauss law of electrostatics is the first Maxwell's equation, integral form of Maxwell's equation, and Gauss law of magnetostatics, that is Maxwell's second equation. Abhi tak you know integral form of that. Now we have it in differential form. So you can say first two Maxwell equations we know in differential form. And now let us look for other Maxwell equations. And let us start with the fundamental laws. This is Faraday's law of electromagnetic induction. We can write it in integral form. We are already aware what is integral form. If we are not aware, we'll write it in a few minutes. And then I'll convert it into differential form, because that differential form is more convenient for me, or it will be more convenient to use that to write wave equation for electromagnetic waves. So this is just mathematics we are doing. You all understand what is Faraday's law of electromagnetic induction. It is about changing magnetic field, changing magnetic flux. If I have field, I can produce magnetic field, and it is linked with some closed loop. This is closed loop. Okay, it is enclosing this area. This area is enclosed by this closed loop, and magnetic flux is linked to this closed loop. Then we see if there is change in this magnetic flux, which I can write. This is magnetic flux, subscript B I'm writing to distinguish it from electric flux, is equals to, this is B dot, if I choose small area, I can say B dot ds. This is not total flux, this is d phi. This is small flux linked with small area ds. And to find total flux, I integrate all such contributions, small contributions, and I say that total is integral of this. And this is now, you should see that this is open integral. This is not closed integral because I do not have closed surface area. This is part of this open area. It is not enclosing any volume. So we can say that this is flux. And this flux changes with time by changing either this or by changing area, whatever it is. But what Faraday's say, it says that rate of change of this flux, whatever is the reason, but the rate of change of flux is directly proportional to directly proportional to EMF produced in the loop. So by moving this magnet or by varying magnetic flux, we see that current is produced or electric field is produced, and you can say EMF is produced in this loop. So this is mathematical form of Faraday's law of electromagnetic induction. And so I can write this as E equals to minus d by dt of phi, where phi is magnetic flux. So phi subscript b is the better way of writing this phi. Now I understand that this phi is integral form of phi, or this flux is this. So I can write that E is equals to minus d by dt of b dot integral b dot ds. Or I can interchange operation of these operators, because this is my differential operator d by dt. I have another operator here, that is integral operator. This is called integral operator. Or this is integral operator. So I can interchange their operation. They are linear operators. Whenever we have linear operators, we can interchange their operation. यहाँ पे B पे दोनों का ऑपरेशन है. We are operating with integral operator first, and then after that we'll be integrating with this. Sorry, we'll be operating with this d by dt. But we can interchange this operation. Then I can write that this is d by dt first, d by dt of b, and then I do integration. Okay, and what about this? This is EMF. I can write EMF as EMF is what it is. What is EMF? Will tell me what is EMF. Quickly. Any one of you unmute and tell me what is EMF.
minus d phi by dt.
नहीं, हाँ, definition वो तो लिखा ही है यहाँ पे, that is written. I'm asking you how you define EMF. If EMF of this, I'm saying that EMF is EMF is produced in this loop. So how you will define this?
Sir, EMF is induced current.
Okay, EMF is what it is work done in moving unit positive charge once around the closed loop. This is how you define in your +2 level या जहाँ पे भी है ना. So I can write that work done. I can write as this is E dot dl. Dl is what it is part of this loop, and this is closed line integral of E. Okay, or it is, you know, that work done hai. This is what work done per unit charge. This is what I am saying. It is EMF is what it is work done per unit charge. So I can write this as what it is F dot ds is the distance, work done is this. Okay, and this is small work done. You can say dw divided by this q naught. It is only work done in moving charge from this to this through this dl. You can say dl, not ds. I should write dl, to this dl distance, and integrating this over the whole loop. That gives you what that gives you. So this is electric field. So I can write this as E dot dl closed line integral of E dot dl. So I'm using this basic definition of EMF to write it as this is closed line integral of electric field. So let me write both the sides in integral form. I can write that EMF, which is closed line integral of electric field E, is equals to negative of surface integral of d by dt of B dot ds. Okay, this is what this is. Faraday's nothing. This is this only, but it is in this form. This is integral form of E, and this is integral form of phi, and then we can see that this is what this is. This is Faraday's law. Now, whenever we see closed line integral or closed surface integral, then we should go for, we can convert that integral according to either using Gauss divergence theorem or Stokes theorem, whichever is applicable. So here we can see this is closed line integral of electric field E. So I can use Stokes theorem, because Stokes theorem, it relates closed line integral of any vector to surface integral of that, or not that vector, but curl of that vector. So let me write Stokes theorem for electric field, or line integral of electric field. So that is what it is. This, and this can be related to surface integral of curl of E dot ds. Okay, this is Stokes theorem. So using this Stokes theorem, I can rewrite left hand side. So it is in the surface integral form. It is curl of E, surface integral of curl of E is equals to, this is this. So now we have what we have on the both the sides. We have surface integral, and I can equate integrands on both the sides, and after equating, because this is arbitrary, so I can equate integrands. So I get curl of E is equals to negative of d by dt of B. The rate of change of magnetic field gives you what? It gives you electric field. This is nothing but this is the same law, that is Faraday's law of electromagnetic induction, and this is differential form of Faraday's second law of electromagnetic induction, and this gives you third equation, Maxwell's third equation in differential form. So let me write again quickly. This is my Maxwell's first equation, or D or B, you can E, you can write it in any form. It is rho divided by epsilon naught. My second equation is divergence of B equals to 0. Now I have written third, that is curl of E. Curl of E is equals to negative of d by dt of B. Then fourth Maxwell's equation, it comes from Ampere's law. So this is what we have done. And next is what it is, Ampere's law. I can write another equation, Maxwell's equation, or fourth Maxwell's equation, starting with the basic Ampere's law, writing it in different integral form, and then converting that integral form to differential form using calculus, what we have done, and then we'll put that as a fourth equation, Maxwell's equation. What is Ampere's law? Whenever Ampere said that he observed that when there is current in any wire, magnetic field is produced around that wire. So current carrying wire can produce magnetic field, and if I is the current running through the wire, then I can see at any point P, I can find what is the magnitude of magnetic field produced. For that, he proposed this, that you draw Ampere's loop. This is Ampere's loop, imaginary loop around this wire of radius equal to the distance between the wire and the observation point. Then he said that closed line integral, closed line integral of magnetic field all along this loop is directly proportional to or is equals to mu naught times I. So magnetic field produced is directly proportional to current flowing through the loop, and it also depends on permittivity of the space or the region. So you can say that this is Ampere's law, and in this we can write this I, because I is current flowing through this conductor. So let me also take into account dimensions of this conductor, and let me say that it is conductor of finite area of cross section, and let me call that area of cross section S or A, anything S. So then we can define, or we can write this current in terms of current density. Current density is defined as what it is, current through unit area of cross section. Okay, so I can write that through ds. If I say that I choose small a, this is the whole cross section, and I choose the small ds cross section of the out of the whole cross section, then I can write that j dot ds is the current flowing through this small cross section ds. And total current flowing through the whole cross section or through this wire is equals to integral j dot ds. Okay, so I can write current as this in terms of current density. So I can write this integral. This is or Ampere's law. This is equals to closed line integral of magnetic field is equals to mu naught times I. So you can write it as mu naught times j dot ds. This is surface integral, whereas this is line integral. And this is closed line integral. So we are doing it again and again. So you can predict now what theorem we can use to convert this into surface integral. We try to convert this into the same integral as we have on right hand side. So on right hand side, I have surface integral so that I can equate integrands on both the sides. So I use Stokes theorem here, and using Stokes theorem, I can write this as a surface integral. This line integral can be written as a surface integral of divergence of this field. So not divergence, curl of this field. So it is curl of B. This is equals to surface integral of mu naught j dot s. Okay, now I can again say that I can equate integrands on both the sides. So I can write that curl of B magnetic field is equals to mu naught times J, where J is current density. So this is Ampere's law. This is same Ampere's law. This is my Ampere's law, and this is Ampere's law, but in differential form. So can you write now all the four? Yes, we can write. We have two divergences: divergence of electric field. I have divergence of magnetic field. I have curl of electric field and curl of magnetic field. Divergence of electric field, according to Gauss law of electrostatics, is rho divided by epsilon naught. Divergence of magnetic field, Gauss law of magnetostatics, Faraday's second law of electromagnetic induction, curl of gives you curl of electric field, which is minus d by dt of negative of d by dt of B. and we have curl of magnetic field according to Ampere's law. It is mu naught times current density J. So these are what? These are Maxwell's four equations and differential form of Maxwell's four equations. Okay, so using these Maxwell equations, and even we have one more thing here, that is modified form of Ampere's law. This law is inconsistent law, and what is inconsistency in this law, and what more is predicted by Maxwell to make it consistent, we'll see that. And how it becomes consistent, we can also verify that. And then we talk about one more law, which is only a modified form of this Ampere's law. And in modified form, it is called Maxwell Ampere's law. And what was that modification? He introduced, we'll go into every detail of that, but usse pehle let me write here that it is. And one more thing, yes, you can see that हमने पहले लिखा it in B form. And now it is what it is. We can write this as mu naught times H. So mu gets cancelled on both the sides. So you can write that curl of H, magnetic field intensity, is magnetic induction, and magnetic field intensity, it is what it is. Curl of H is what it is, J. Okay, we modify this, and what is modified version? It is curl of H is equals to, this is what current? This is conduction current. This is current flowing on a wire. अभी तक हमने जो law किया Ampere's law, in that we talk about current running on a wire. This is what? This is current due to flow of charge carriers. Some electrons, charge carriers are flowing, and due to flow of these charge carriers, we have conduction. Part. So we talk about displacement current. This is conduction current, and we have displacement current. And what this displacement current is, it is not due to flow of charge carriers, but it is due to time varying electric field. So we can see that earlier we said that Faraday said that time varying magnetic field d by dt, this produces what? This produces E, you can say EMF, or you can say indirectly, or this produces what? This produces electric field. There is some electric field is produced due to time varying magnetic field, and other way around is according to this this law, that is Ampere's law, that time varying electric field, it also gives you what? It gives you magnetic field. You'll see that what we mean by all this. So what I'm saying is the magnetic field is not only produced by conduction current due to flow of charge carriers, but there is one more contribution to this this magnetic field, and that contribution comes from displacement current, and that is what? That is d by dt of E. Whenever the displacement current is there, whenever we have non-zero rate of change of electric field. If electric field is what it is, not time varying, then you will say that there will be no contribution to magnetic field. It will not produce any magnetic field. But if we have time varying electric field, so then we can expect magnetic field, and that is to that we give relation that how it is related. We say that displacement current is what it is, epsilon naught times d by dt of electric flux. So in any space, free space or any, whenever there is what? There is a rate of change of flux, electric flux, है ना? यहाँ पे भी हमने rate of change of flux से बात शुरू किया था. It was rate of change of magnetic flux, which is giving you producing electric field. So here rate of change of electric flux, okay, it produces what? It produces magnetic field. And this is given as magnetic field is related to current, so we say that it is some this is what some displacement current which is producing what, which is producing electric field. So we can say that if I write that modified form of Ampere's law, so let us start it with that integral form. It is this mu naught times J. Earlier it was only mu naught times I. Okay, and this was only conduction current. Now with this we have introduced one more reason for uh, magnetic field, and that is what, that is displacement current, and which is related to magnetic field in a way that it is the rate of change of electric flux, or it is proportional to rate of change of electric field. So this is my modified version of Ampere's law. This is modification. ID is the modification in this law. And this modification was suggested by Maxwell. That's why this is not called now Ampere's law. This is called Maxwell Ampere's law. Ampere's law. So differential form of Ampere's law is this. And differential form of Maxwell Ampere's law, we need to write. So for that, quickly, if I do, it is what it is, B dot dl is equals to mu naught times conduction current. हमने पहले लिखा conduction current is what it is, integral J dot ds plus we have what, we have displacement current, and I said that it is epsilon naught times d by dt of electric flux. So electric flux is integral E dot ds. Okay, this is electric flux. As I said earlier, I can interchange operation of operators, integral operator with differential operator. I can take this inside this integration because this is independent of ds. So I can write it as mu naught times sum of integrals. This is J dot ds surface integral, plus you can write this as let me keep it simple. Let me write this is epsilon naught times, or as I introduced, epsilon naught times E is electric displacement vector. So let me write it as d by dt of d. This is what this is. D is electric displacement vector epsilon naught times E. I'll explain to you what this is. So dot ds. I can club these integrals because both are surface integrals. So I can write, because integral operator is a linear operator. So I can say that I can club, I can write it as integrand, common integrand can be written. It is, sorry, plus d dot ds. Okay, this is equals to this. Okay, and as you did earlier, you can convert this from line integral to surface integral using Stokes theorem. Then you write it as, this is surface integral of curl of B, or B is mu naught times H ds. This is equals to now this, and we can do what, we can equate the integrands as both are surface integrals. So equating integrands on both the sides, if I equate integrands on both the sides, let me write it here now. I can write my final result. I can write Maxwell Ampere's law in differential form, which will be the fourth equation, Maxwell's fourth equation, or that will complete the four equations pool. So I can write that it is this is equating integrands. So it is curl of H mu naught, I'm writing outside, I'm writing this, is equals to integrand on this side is mu naught is there, and inside square square brackets, I have integrand that is J plus d by dt of electric displacement vector. I can cancel this with this. So my modification is what? Earlier it was only J. This is the MPS law. This is MPS law. But if I add this term to MPS law, this is time derivative of electric field. D is related to electric. So you can say this is time, or let me write it as epsilon naught times Z. This is this. So I have what? Magnetic field is produced by this. That is current flowing on a wire, conduction current due to charge carriers. Not only this, there is contribution to magnetic field due to electric field, time varying electric field, which is not flowing charges, but it is electric field which is varying, which is time varying. So this is what this is. This is Ampere's. Sorry, this is Maxwell's contribution, and this is Maxwell Ampere's law. So all the four laws you can write quickly. It is, let me write them quickly for you. This is divergence of E, which is rho divided by epsilon naught. Divergence of B, which is 0. Curl of E, which is negative of d by dt of B. And I have now fourth equation, and that fourth equation is curl of H with modification. This is this, but with modification, we should write it as this. So I have these four equations in differential form, and these are famous Maxwell's equations. We'll be using these equations. We have done nothing but basic fundamental laws of electricity and magnetism, and using these fundamental laws, why Maxwell combined them all or used them all together to explain unification of electricity and magnetism. And this gives you what? That electric field from, you can see that third equation, rate of change of B is producing E, and from fourth you can see rate of change of E on right hand side. Rate of change of E is what it is. This is rate of change of E is giving you H field or B field. Okay, so let us end today's lecture here only. It is already 2, and if you have anything to ask, any queries, you stay back, you ask your queries, and rest of you can hang up.